Pluto is a faraway and unpretentious yet truly certifiable planet that was once a part of our planetary framework. However, recent statements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They proposed that this distant world might be on a potential impact course with Neptune. But how could this truly happen? What might be the consequences of such a massive event? Are we witnessing an impending cosmic catastrophe, or is there more to this looming celestial collision? Join us as we examine the scientific possibilities of a Pluto-Neptune crash. Pluto, a former planet reclassified as a dwarf planet, remains a subject of intrigue in the vast universe. According to recent theories by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are raising alarms about a potential catastrophic collision between these two celestial bodies, which could have significant ramifications for Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, Pluto has not yet completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its highly eccentric shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unique is its inclination, which is 17 degrees to the ecliptic plane. The way Pluto follows its path is far more erratic compared to other planets. This inclination and eccentricity add layers of complexity to its orbital structure. One of the most fascinating aspects of Pluto's orbit is its relationship with Neptune's. For about 20 years during each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its peculiar path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and irregular shape. Eventually, it was recognized that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit, despite these complexities, is a testament to the intricacies of celestial mechanics. The three-body problem in space involves determining how three objects, such as Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like predicting their movements based on their starting positions and the gravitational forces they exert on each other. For Pluto, this problem reveals how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex manner. Key terms like non-synchronous libration, orbital precession, and VZK wobbling are critical to this puzzle. As explained by astrophysicists, non-synchronous libration between Pluto and Neptune means that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from overlapping. Orbital precession, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is located far above their orbital plane, adding another layer of safety against potential collisions. Another key factor is VZK wobbling, named after three scientists, V, Z, and K, who studied the motion of celestial objects. This wobbling describes how Pluto, Neptune, and the Sun exert gravitational forces on each other, influencing Pluto's erratic movement near the Sun. Despite Pluto's seemingly chaotic orbit, this wobbling maintains its stability over long periods. The VZK wobbling demonstrates that even in the seemingly wild universe, patterns and rules create order. These forces ensure that Pluto's orbit remains stable, preventing it from colliding with Neptune or drifting off course. The three-body problem is central to understanding how these orbits evolve under gravitational interactions. Studying this helps us learn more about Pluto, our solar system, and even distant worlds and their stars. Mathematical simulations in the late 1980s revealed that, despite its stabilizing features, Pluto's orbit is actually unstable. Small changes in initial conditions could lead to large differences over centuries. However, these irregularities in Pluto's orbit have been shown to maintain stability over incredibly long timescales. Recent digital computations have provided insights into how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's orbit. Around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. But Neptune isn't working alone. Jupiter's massive gravity also plays a crucial role in stabilizing Pluto's orbit, with Saturn contributing as well. These findings suggest that Jupiter's gravitational pull is strong enough to ensure Pluto remains on a steady path, perhaps indefinitely. It seems Neptune, Jupiter, and Saturn work together to ensure Pluto continues its safe journey through space without running into trouble. These forces are vital for maintaining order in the inner solar system. Without these stabilizing forces, our solar system could be much more chaotic. Bodies like Pluto could collide with others or be ejected from their orbits, triggering a chain reaction with other celestial bodies. For Pluto, especially in light of discussions about its potential impact with Neptune in the future, understanding its orbit is crucial. This provides a clearer picture of the dynamic nature of the solar system. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve a state of harmony through the intricate interactions of gravitational forces. The delicate balance between these forces ensures the stability of Pluto's orbit and its unique relationship with Neptune. While the possibility of a collision between the two may sound alarming, the dynamics of their orbits make such an event highly unlikely in the near future. The resonance between Pluto and Neptune ensures their orbits never meet directly. This special relationship is the result of millions of years of gravitational interactions that have shaped the paths of celestial bodies in the solar system. It's a testament to the intricate dance of planetary mechanics, where chaos eventually gives way to order over vast timescales. Furthermore, advanced simulations and numerical modeling continue to refine our understanding of these interactions. Astrophysicists use supercomputers to simulate the movements of Pluto, Neptune, and other bodies in the solar system over billions of years. These studies not only reveal the stability of Pluto's orbit, but also highlight the resilience of the solar system as a whole. In conclusion, despite its reclassification as a dwarf planet, Pluto remains a source of fascination for scientists and the general public alike. Its icy surface, mysterious atmosphere, and eccentric orbit offer clues about the formation and evolution of the solar system. As we continue to study Pluto and its interactions with other celestial bodies, we gain deeper insights into the forces that govern the universe, from the tiniest particles to the largest galaxies. For now, the prospect of a crash between Pluto and Neptune remains a theoretical curiosity rather than an impending threat. The gravitational shields in place, including resonance and orbital precession, ensure that these two celestial neighbors maintain their fragile equilibrium. Pluto's story serves as a reminder of the beauty and complexity of the universe. Its orbit, though capricious, illustrates how harmony can emerge from the interplay of gravitational forces. As we explore the mysteries of space, Pluto will undoubtedly continue to inspire wonder and curiosity for many years to come. Additionally, orbital mechanics highlight the importance of ongoing observation and analysis of these peculiarities to better understand our place in the cosmos. Exploring the significance of space often leads us to confront the extraordinary nature of celestial bodies. For instance, Pluto's orbit is an excellent example of this anomaly, the concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions. This is clearly demonstrated by Pluto. For Pluto, this means that even slight changes in the dwarf planet's position or speed can drastically alter its long-term orbit. Using automated simulations has been incredibly valuable for researchers in understanding how Pluto moves through space. These simulations employ complex mathematics to model how Pluto and other space objects, like Neptune, interact gravitationally. By tweaking small details in the simulations, space scientists can observe how even minute changes can result in vast differences in Pluto's eventual position. In the late 1980s, these simulations revealed something intriguing about Pluto's orbit. Despite having stabilizing features like asynchronous libration and orbital precession, Pluto's orbit can still be inconsistent and unpredictable. Even a slight variation in Pluto's position or speed at the start can lead to an entirely different outcome within just a few years. Yet, despite this chaos, Pluto's orbit remains stable over immense timescales, spanning billions of years. This demonstrates that Pluto's journey around the Sun follows a certain order, even though it may appear tumultuous at first glance. Predicting celestial movements, particularly for objects like Pluto, involves understanding these subtleties and complex forces. Despite the apparent chaos in Pluto's orbit, it's clear that underlying forces are at play, maintaining a delicate stability. While small perturbations might cause deviations in its path over shorter timescales, the overall structure of Pluto's orbit remains remarkably consistent over billions of years. These long-term studies emphasize that the seeming unpredictability of celestial bodies like Pluto can often be the result of complex, yet ultimately predictable, interactions. The complexity of Pluto's orbit also highlights the importance of mathematical modeling and computer simulations in modern astronomy. With the aid of supercomputers, astrophysicists are able to simulate the interactions of planets and dwarf planets over vast periods of time. These models help to refine our understanding of the forces at work in the solar system and beyond. Through these simulations, scientists can explore a range of scenarios and test hypotheses about how minor changes in the solar system might affect Pluto and other distant objects. As our understanding of Pluto and other celestial bodies continues to evolve, so too does our appreciation of the fragile nature of our solar system's stability. The careful balance maintained by gravitational forces among the planets, dwarf planets, and other objects ensures that the system remains cohesive, despite the many forces that act upon it. Even seemingly small forces, like the gravitational pull of distant Neptune or the influence of Jupiter, play a crucial role in keeping Pluto's orbit steady. This interconnectedness is part of the broader picture of how planetary systems form and evolve. As scientists continue to study Pluto's orbit and its interactions with Neptune and other planets, they also gain insights into the processes that govern the behavior of other solar systems in the universe. The study of our own solar system serves as a valuable model for understanding the broader cosmic order, helping us to answer fundamental questions about the nature of gravity, motion, and celestial mechanics. Looking forward, Pluto remains a focal point for research. Its reclassification as a dwarf planet has not diminished its scientific significance. In fact, it has sparked a renewed interest in the study of objects at the outer edges of our solar system. As new technology allows for deeper exploration of the Kuiper Belt and other distant regions, we will continue to learn more about Pluto and its place in the solar system. In addition to its scientific value, Pluto serves as a reminder of the ever-changing nature of our understanding of the cosmos. Just as its status as a planet was revised, other astronomical discoveries may challenge our current views and inspire new theories. The exploration of space is an ongoing journey, one that brings new revelations and shifts our perspective on the universe. In conclusion, while the possibility of a collision between Pluto and Neptune remains extremely unlikely, the study of their relationship provides invaluable insights into the complex dynamics of celestial mechanics. It underscores the importance of ongoing observation and research to better understand the forces that shape our solar system and the universe. As we continue to explore the mysteries of space, Pluto will undoubtedly remain a source of fascination, offering new discoveries and lessons about the workings of the cosmos.